Hello everyone. Welcome back to this lecture series on structural mechanics. In the previous lecture, we studied Euler's theory of buckling where we derived the critical load for long columns which are subjected to axial compression, and we understood the influence of end conditions as well as effective length. In today's lecture, we will apply the Euler's theory to practical numerical problems. So through this example, we will understand how to identify the correct end conditions, how to compute the effective length, as well as how Euler's formula is used to find the safe load, critical load, or the geometric parameters. This is lecture number 4, and the topic is analysis of columns, in which the application of Euler's theory has been used. All problems discussed today will involve long slender columns where failure occurs by elastic buckling rather than crushing. Here, a solid round bar 60 mm in diameter and 2.5 meter long is used as a strut. So one end of the strut is fixed while its other end is hinged. Estimate the safe compressive load the strut can carry using Euler's formula. Assume E is equal to 200 gigapascal and the factor of safety as 3. Right. So here the most important step is identifying the end conditions. For a column with one end fixed and the other end hinged, the effective length will be calculated as L divided by root 2. Here L is given as 2.5 meter. So 2500 divided by root 2 will give the equivalent length or the effective length, which is 1767.77 mm. So this means the column is more stable than a pinned end columns if both the ends are pinned, but less stable than a fixed end column. Now the moment of inertia will be calculated. So moment of inertia will define the cross-sectional properties, or otherwise it will give the resistance against the bending properties. So since this is a circular section, we know that moment of inertia will be equal to pi d power 4 by 64, where d is the diameter of the cross section. So here the diameter is 60 mm being given. Therefore pi into 60 power 4 divided by 64 will comes as 636.17 into 10 power 3 mm power 4. Now the crippling load as per the Euler's theory is being calculated as pi square EI by LE square, where LE is the equivalent length of the column. So here LE is being calculated as 1767.77 mm, where E is being given as 200 gigapascal and I is being computed as 636.17 into 10 power 3 mm power 4. So substituting that value, and again one more thing is that here it's been given as gigapascal. So we are supposed to write everything in terms of Newton and mm, in the sense it is nothing like we need to write in terms of megapascal. So because megapascal is equal to Newton per mm square. So here giga has been given, that is nothing like 200 into 10 power 9 pascal. This can be written as 200 into 10 power 6 megapascal. I'm sorry, it should be 3 only, 3 into 10 power megapascal. So that is what has been written here. It will be 200 into 10 power 3. Right. So 200 into 10 power 3 will give the value in terms of megapascal. And I is being calculated 636.17 into 10 power 3 divided by the equivalent length, which is 1767.77 squared, which will give the value as 401.84 kilonewton. But in this question, it's not we need to find the crippling load. Instead, we need to find the safe compressive load. Now the question is, why factor of safety is used? So here the Euler's formula will give the critical buckling load. But in design, we never allow the column to reach the buckling. Hence, the safe load will be calculated by dividing the critical load or the crippling load with the factor of safety. Here the factor of safety is given as 3. Therefore, safe load will be 401.84 kilonewton, that is a crippling load, divided by factor of safety 3, which will be calculated as 133.95 kilonewton. So this problem is a typical one of struts in frames or compression members in industrial structures. And it shows how support conditions alone can significantly change the load capacity. Now let us consider the second numerical example. Here, a slender aluminum column has been given. The length has been given as 1.5 meter. Outside diameter of the column is been given as, outside diameter is given as 60 mm. And it's been given both the ends are pin. The column is subjected to an actual load has been applied as 15 kilonewton. Right. And we are told that the critical load must be twice the actual load. The material property is being given as E is equal to 70 gigapascal for the aluminum. Here the question is, we are required to determine the internal diameter. Right. So this problem demonstrates the design against the buckling. Instead of finding the load here, we are designing the geometry of the column. Now, since both the ends are pinned, the equivalent length or the effective length will be equal to the unsupported length itself, which is as such same 1.5 meter, that is 1500 mm. Here the condition is given as P critical will be equal to twice the actual load. So for which first let me calculate the moment of inertia. So here moment of inertia for not a solid circular column, instead it is a hollow circular column. That is why the formula has been taken as pi by 4 into capital D power 4 minus small d power 4. So capital D is outer dia and small d represents the inner dia. So here the outer dia has been given, which is given as 60 mm. And the inner dia only we are supposed to find it out. So keep it as such small d itself. So we'll be getting the moment of inertia as such. Right. Now the crippling load is being given as twice the actual load. The actual load is being given as 15 kilonewton. So crippling load, which will be equal to twice the actual load, which will be equal to, as per the Euler's theory, pi square EI by LE square. So keep that pi square. E is being given as 70 gigapascal, which is nothing like 70 into 10 power 3 megapascal. So we can write that one. Into I, we can write the same thing. Pi into 60 power 4 minus small d power 4 by 64 divided by the equivalent length is 1500 square. So now the left side is 2 into 15 into 10 power 3. Right side everything is known except the small d value. Now solving this one, we can get the internal diameter as 57.55 mm. Here, why hollow columns are used? So once if you are using the hollow columns, it will reduce the weight of the structure as well as it will maintain the stiffness and economical use of material. So this problem highlights how moment of inertia, not area alone, governs the buckling resistance. Let us move to the built-up I section for this being considered in this problem. So given us the web size is 25 mm by 900 mm. Right, the thickness is 25 mm and the height is 900 mm. The flanges are 320 mm by 60 mm. So 320 mm by 60 mm. Both the sides are same. It is being simply supported at ends. It's a beam, first of all. It's a beam. It's a built-up beam of I cross section, which is being subjected to an UDL of 50 kilonewton per meter. And the measured, due to this loading, the beam deflects by 7 mm. We are asked to compute the length of the beam. Right. We need to compute the length of the beam. And second thing is that estimate the safe load. Estimate the safe load if the same member is used as a column with both the ends fixed. Right. The same beam is being converted as a column with both the ends fixed. This is a very important problem because it connects the beam theory with the column theory. Now, the first part is uses the deflection theory of beams, which will helps to determine the span. Here in this case, it is simply supported beam subjected to UDL. So in that case, the maximum deflection will be calculated by using the formula delta max will be equal to 5 divided by 384 WL power 4 by EI. That's what has been written here, the maximum deflection, for which we need to find the required values. The maximum deflection has been given 7 mm. The left side 7 mm has been given. Regarding the right side, the W has been given, that is 50 kilonewton meter has been given. So kilonewton per meter, which is equal to Newton per mm. Kilonewton per mm. Sorry, 50 kilonewton per meter, which will be equal to 50 Newton per mm. Keep it as such. So L only we are supposed to find out. Regarding E, it's been given 200 gigapascal. This is nothing like E is equal to 200 into 10 power 3 megapascal. And regarding I, we are calculated because it's an I section and you can see it is a symmetric section. So we don't need to find separately for all these elements by using the parallel axis theorem and all. Since the section is pure symmetric, we can consider it as a full rectangular section, a solid rectangular section of size 320 by the total length is 1020. 900 plus 60 plus 60. So that is the overall cross section. Right. So that is how much? 320 into 1020 BDQ by 12. Minus this area, the moment of inertia to be removed. That is, since it is a symmetric section, we can take both separately. Instead of separately, we can take it all together. That is, overall thickness is width is 320 minus 25. So you'll be getting that width is nothing like 295. This is this plus this will give 295. That is nothing like this is 295 by 2. This is 295 by 2. So the total is 295 and the total depth is 900 mm. So this will be minus into 295 into 900 cube divided by 12. That is what has been written here for calculating the moment of inertia. But this condition is applicable only if the overall cross section is pure symmetric with respect to both axes. So we calculated the moment of inertia as 1.04 into 10 power 10 mm power 4. Now regarding this one, so W is known, E is known, I is been calculated. So substituting everything, we can calculate the unsupported length as 12.229 meter or otherwise 12,229 mm. So here, the second part is I need to convert this beam as a column. Right, we need to convert this as a column and we are going to apply the Euler's buckling formula. So since both the ends are fixed, the equivalent length of the column will be half of the unsupported length, that is L by 2. That is 12,229 divided by 2, which will comes as 6,114.5 mm. So we got the equivalent length. Right. Next thing is that E and I are known, I to be found out because we need to find the maximum one for finding the crippling load. So for which we are taking with respect to the YY axis, that is we need to find the minimum of those two. So for which we are taking the YY axis, because YY axis in the sense total is 1020, the total depth, and the width is 320. So this is what will give the minimum value. So that is the reason we are going with the IYY. So since IYY if you are going, it is not symmetric. So in that case, what we are going to do is going to take the elements separately. We have two flanges and one web is available. Right. Let me start with the flange. So here we are going to use IYY. So in that case, it will be DBQ by 12. So here D is 60, and B is 320. So that is why DBQ by 12. That is 60 into 320 cube divided by 12. And since we have two elements are there, so it will be multiplied with the 2. And again, it is symmetric. We are not going with the second part of the parallel axis theorem, that is A into x bar square. It is symmetric because this section is symmetric about the axis. So x bar of this flange section and the x bar of the I section coincide. So the second component will be 0 for both flanges as well as the web. So now moving on with the web, again DBQ by 12. So for the web, D will be equal to 900 and B will be equal to 25. So substituting this one, it will be 900 into 25 cube divided by 12. We will get the IYY as 328.85 into 10 power 6. Remember, we already calculated IXX, which comes in the form of 10 power 10. That is a maximum one. So since we are going to calculate the crippling load, that is a maximum one. So the denominator should be minimum. That is the reason, the numerator should be minimum. So that only, once if it is exceeding, the column will be failing. So we are calculating for the minimum value of the moment of inertia. So pi square, E is known, I has been calculated, and the effective length has been computed as 6114.5. So substituting everything, we have calculated the crippling load as 17,362 kilonewton. So now the question is not only the crippling load, we need to find the safe load also. So safe load will be equal to crippling load divided by the factor of safety. So we'll get that value as with a factor of safety of 3. The safe load is being calculated as 5,787 kilonewton. So now the importance of the factor of safety is, again, the Euler's critical load is divided by here with a factor of safety 3 to obtain the safe load. So this problem is highly relevant for columns in industrial buildings as well as built-up steel members. Now, let us consider the final example, which is very important from a theoretical and exam point of view. Here, we are asked to determine the maximum slenderness ratio for which Euler's formula remains valid. So, the given thing is material is mild steel, right? The material is mild steel, the column. Yield stress is being given as 3000 meganewton per meter square, or otherwise 300 meganewton per meter square, or otherwise nothing like 300 megapascal. Both are same, because Newton per meter square is equal to Pascal, and this is equal to 300 Newton per mm square also. And the modulus of elasticity is being given as 200 gigapascal, so which is equal to 200 into 10 power 3 Newton per mm square. Now here the conceptual basics is, before going with this one, since the column is pinned, assuming that the columns, both the ends are pin ends, the equivalent length will be equal to the unsupported length. And since the column buckles at the stress which are lower than the compressive yield stress sigma c of the material of the column, it follows the Euler's formula will be valid so long as sigma cr will be less than or equal to sigma c. Right. So here sigma cr is the crippling load, and sigma c is the yield stress. Right. So that is, the buckling must occur before yielding. Right. So now we are using the Euler's theory. Right. We are using the Euler's theory, that is sigma cr will be equal to, or PCR. We know that PCR is equal to pi square EI by LE square, in which we know moment of inertia can be written in terms of A into K square, where K is the radius of gyration. Right. So once if you are substituting the value of I as A into K square in this relationship, we'll be getting pi square E into AK square divided by L square, or otherwise LE squared only. So now we know buckling stress is sigma cr, which will be equal to load by area, the crippling load divided by the area. So substituting the values, we know that PCR has been calculated as pi square E AK square divided by LE square, and the denominator we are going to add area, right? So already area is available, that is here I can write it this one. So sigma CR will be equal to pi square E AK square divided by LE square is there, and denominator A should also be added. So A can be added. So this A and A will be getting cancelled. This will be equal to pi square E K square divided by L square. And again, bringing that K to the denominator, we'll be getting this one as pi square E divided by L by K whole square. That is what has been written here. Pi square E divided by L by K whole square. Now, this has been given, the condition as should be less than or equal to the yield stress, right? This should not, this should be less than or equal to the yield stress. That is, Yield stress has been given as 300 megapascal. So pi square E divided by L by K whole square, which should be less than or equal to 300. In this case, since we are assuming the material is a mild steel or it has been given, so E will be equal to 200 into 10 power 3, that is 200 gigapascal, or otherwise 2 into 10 power 5 Newton per mm square. So now we are bringing this one to the right side, and this 300 has been brought to the denominator, so that pi square E is being written as 200 into 10 power 3, and 300 will be coming to the denominator, so that the right side will become L by K whole square. That is, here you can see that we have L by K whole square, which will be coming on the right side, so that should be greater than or equal to pi square into 200 into 10 power 3 divided by 300. So solving that one, will be getting L by K whole square should be greater than or equal to 6579.74, and taking square root on both the sides, L by K should be greater than or equal to 81.12. So here, this is what is L by K. L by K is nothing like the slenderness ratio. So hence, for a column with a hinged ends, the Euler's formula is valid for the slenderness ratio of greater than or equal to 81.12. So this problem defines the boundary between the long and the short column. So if the slenderness ratio is high, Euler's theory is applicable. Whereas if the slenderness ratio is low, crushing or inelastic buckling will dominate. And here we use the radius of gyration, right? So this buckling depends on least radius of gyration and weak axis of bending. So column always buckle about the axis with a minimum stiffness. Now let us summarize today's lecture. Euler's theory is applicable to long columns. Correct identification of the end condition is most critical part, and the effective length governs the buckling strength, where factor of safety converts the critical load to the safe load. And this Euler's theory is valid only behind a limiting slenderness ratio, as well as the geometry and moment of inertia plays a dominant role in column design. Thank you.